Okay, so I'm trying a Cam Studio program to see if this will help us be able to give you some insight that we weren't able to get to in class because of time. So I'd like to start by looking at the zero resultant force example, and you'll notice this is very similar to one I gave you in the pre-quiz. In this particular case, we're dealing with metastable equilibrium. That is, where is the point where this um, charge Q3 is exactly zero force on it. And so there'll be an attractive force from the left and an attractive force from the right. The directions will be opposite because they lie on either side of the negative charge. When we do this work, we're going to get a quadratic equation. In this particular case, it's going to be a particularly simple quadratic equation. And when we get done, we'll choose the root that places the charge between Q3 between Q2 and Q1. In other words, it's got to be between these two in order to be balanced. Okay, so we put in the actual charges for the problem, but we're not going to substitute them in until we derive our own formula that we can use to solve for the position of the particle. So we know that F3, that's the sum of all the forces on Q3, is going to be F13, the attractive force towards Q1, and F23, which points in the opposite direction towards Q2. At this particular point, we're going to write them as absolute value signs and put the signs of the force in by hand. So this black line here stands for the y-axis, and this horizontal black line stands for the x-axis. Since everything's on the x-axis, we only have to write our forces in terms of their I component. And F23, pointing to the negative I direction, we put in by hand the sign over here of minus K electric Q2 times Q3, absolute values, over R squared. In this case, R is X, so it's X squared. And then we add to it the force from the first charge, so that's F13, and that force points to the right. So we have K electric, and then the product of the absolute magnitude of both of the charges divided by the distance that they are from Q1, and that distance is 2 minus X, and it's quantity squared because the force law goes as 1 over the distance squared, not 1 over distance. And again, this is in the I direction, and everything is equal to 0. Well, we can simplify this equation because we can take one of the terms over to the other side and work at our signs to make everything pleasant. And there is that equation. Then we can cross multiply by those quantities that are in the denominator. That's x squared and 2 minus x quantity squared. And we can cancel out x, the x sub, or q sub 3, and the k quantities right here. And that leaves us with this equation right here. And you can see that we're well on the way to solving that because we can take a square root of both sides and reduce it to a linear equation where we've got 2 minus x times the square root of the absolute magnitude of Q2, and that's equal to plus or minus x square root of Q1. And the plus or minus came in because when we take a root we could have either the minus of this quantity squared equal to the quantity x squared q1, or plus yielding that. Now you might wonder, why don't we put a plus or minus on the left hand side as well? Turns out that would be redundant, giving us 4 roots, but only 2 of the roots are unique. And so just putting a plus minus here on the right will do the job for us. Okay, now we're going to go ahead and solve it. And that yields the quantity you see on the right there. Now we'll substitute in for the actual values we have, which are 6 and 15 microcoulombs. And when we get done, we have that the position is 0.775 meters for that charge. And as we guessed, it would be closer to the smaller charge, which is Q2 here on the right, or on the left, and it would be farther from the 15 microcoulomb charge on the right. Now, what would have happened if we had taken the minus root? Well, if we had, and that should say, yeah, and it says that right. If we'd taken the minus root, we would have gotten a value of x is minus 3.4. And if we look at that spot, we'll see that there would be a force, 2 force vectors to the right. But that's not a solution, since that's a place where the force vectors are equal, but they're in the same direction, not in opposite directions. Okay, now we go from the one-dimensional example to a two-dimensional example, and in general this could be put to a 3-dimension. Here in this case we're going to ask, what is the force on Q3? So Q1 exerts a force on Q3, and the r vector that takes us from 1 to 3 would be written r13, and it points in this upper right hand direction. And when we add that concept to the force, we have that the force also goes to the upper right hand direction. Because both of these charges are positive, they'll give us a product which is positive, and so the force will be in the same direction as r13. Okay, here to the left, the situation is reversed a little bit, because the product of Q2 and Q3 is negative, and so we'll have an attractive force. R23 would be also to the right, but because of the negative sign, the force is back around here to the left. And we can add those forces up in a vectorial fashion. But that means it's now time to think about vectors, okay? A student had asked me, what can I do to catch up on everything I forgot during my mission? And I recommend Shalm's outline, which is what I did almost 50 years ago when I got back from my mission. But there's a lot of online things now that are programmed helps. I'm wondering if the Khan Academy would have some of the things that you would like to learn. So what are we going to do today? Well, we're now going to do vectors. All right. We're going to look at their definition, their notation, and operations that deal with them. A vector in biology means that means by which a disease is carried from one individual to another. And that's a similar definition to what we use in physics. We're interested in the force that carries an influence from one particle to another. And by the way, I can give you an account as to why forces act the way they do, which I didn't do earlier because of time, but I'll do that on a separate video someday. Okay, so mathematicians will define a vector as a column of numbers, and so that's what is depicted over here. That's saying this cap, or this V boldface, that's one symbol for a vector, is a series of numbers. Well, we can interpret those series of numbers, being physicists working in 3 dimensions, as how much do we go in the x direction, how much do we go in the y direction, and how much do we go in the k direction. In this particular case, these are velocities, so we could plot this on a velocity diagram or on a regular Cartesian position diagram where these are the derivatives of the velocity. Notice the symbol we use for going in the x direction. It's a cap letter I. And a letter I with a hat on top of it. And similarly, we have J with a hat on top of it and K with a hat on top of it. Those symbols with a hat on top are unit vectors. And we can think about unit vectors for any vector. What we do to get a unit vector, as written down here, is we take the vector and divide it by its magnitude. Alright, so for example, we've got a vector called I plus 2j plus 3k. So we write the value of r on top, that's the I plus j plus k components, and in the numerator we write down what the magnitude of r is, and that is given by the Pythagorean theorem. It's the square root of how much we go in the x direction, 1 squared, plus how much we go in the y direction squared, that's 2 squared, and plus how much we go in the z direction, again quantity squared. When we sum all those together, we're going to get 14 and take its square root. And then these particular coefficients are the coefficients for the unit vector pointing in the same direction as r. And we use this a lot in physics, so you're going to need to pay attention to how this is done. And okay, so vectors can be added, subtracted, or multiplied by regular numbers, and regular numbers are scalars, and they can be multiplied by each other in two different ways. We'll talk about one today. Alright, so for example, the force vector F, which is the total force, is the sum of F1 plus F2. Now, this is just a particular case. It's not any particular problem we're doing yet. But notice that each of those vectors, 1 and 2, could have been written as a sum of one vector 1 in the x direction, vector 1 in the y direction, and vector 1 in the z direction. Each of those would have been times the direction they are in Cartesian coordinates, that is along the x direction or the y direction or the z direction. The same thing can be done for vector 2, and then we can collect together the x components, in other words the ones that have in common I with a hat on top, and that's given by this formula here, that the I component will be f1 sub x plus f2 sub f sub 2x in the I direction, and similar vector components in the j and k directions. Okay, the notations we have for vectors are boldface, and I'll use that a lot because it's easier for me than going into math mode every time I want to do a vector. And we could do it with arrows. That requires the math mode, or hats or carets, as we do for unit vectors. The handout gives you some sample problems to do. There are some typographical situations on the second page where evidently my character set mutated between the last time I printed this out and today, and I'm going to talk more about that to you later. You'll note on the second page of that handout, and that's where the difficulties are, that you should never use the cross product to get the angle between two vectors. Instead, we're going to use the dot product. Okay, subtraction is just like addition, but you take one of the vectors and put minus in front of everything you do. But the reason why I want to talk about it here is that the position vector r12 is really important, because that's a vector that we use to indicate the influence that charge 1 right here on our set has on charge 2 over here on our set. And the way we talk about all vectors is by a subtraction phenomena. And so what I want to do is think about the definition of a change in a quantity. And the mantra that you should always memorize and remember is you take the final position, that's over here, which is the position for Q2, which is also called R sub 2, and you subtract from that the position that's causing the force. We also can call that our initial when we're doing deltas. And that position, if we're on a Cartesian coordinate system, would be R1. Okay, that's a really important way of doing things. We'll do it a lot. So again, the formula we need to remember whenever we're doing differentials, which come to be derivatives, or if we're doing the vector that tells us of the influence of 1 on 2, it's final position or final quantity minus initial. Delta equals final minus initial. Okay, so now we're going to talk a little tiny bit about homework problems. Remember, homework problems are submitted online at the Max website. Some of you have gotten to Max through Learning Suite, but the Learning Suite app for your cell phone won't work in taking you to Max. So you need to go to Max if you're using a cell phone by using your browser. The website provides data that is unique to you and for each attempt that you make. The reason why we use Max rather than Learning Suite is because of this. Learning Suite didn't use or didn't have the option to provide unique data to the students with each attempt and to each student. So Michael Ware created our own version of that does that particular function. Number 2 is, remember that multi-part problems have 2 points each and they're scored independently. That means you can submit each part as you go along, though I advise you finish all parts of a problem before hitting the submit button. Otherwise you'll get new data for the rest of the problem, and that'll mess you up. Don't come back to me and saying, well, yeah, it messed me up, please give me the points back. I can't do that. It's too hard based on the way the program does its grading, which is automatically takes what you got on the problems and puts that in. You only get one attempt on multiple choice problems, so remember that. Choose wisely. Alright, here's one of the problems that we have to do, and the data that they gave me for my doing of the problem is right here. I've got that the y component is minus 2.11 in the and that'll be in the j direction. And one of the questions it asks us to do is to calculate the magnitude of r. So I've put in some text here, maybe, to do that. It doesn't look like we're going to do it today. We'll do it later. Instead, we're going to go to the next question, which is, can we understand how to do products of vectors? And so we're going to go to chapter 7, where we did work, and talk about what component of a vector is along the direction of acceleration for the vacuum cleaner. This fellow is doing his assignment at the church on cleaning up, and as he walks down the hall, he pulls on the vacuum cleaner cord, which makes a 30-degree angle to the ground. And we know that not all of his force, all of his 50 newtons of force, is going to go into accelerating the vacuum horizontally. Some of it goes into reducing the normal force because there'll be a component in the same direction as the normal force. And we know that normal force plus that component are equal to mg. And you know that's true, that if you were too close to the vacuum cleaner and tried to move it, you would just pull it upward. So you know that it's got to be a component. We have to break the vector up into two components. So here it is. This is the free body diagram. It shows that the normal force plus the component in the vertical direction of the force that I'm supplying while I'm vacuuming the church will be equal to mg. And for our problem today, we also know that the horizontal component, which is going to be related to cosine of 30 degrees, is going to give us that component. So now we're going to simplify it. We've taken away the vacuum cleaner, and what's causing the forces we've just written down a free body diagram that shows you what happens. Okay, so the normal force and gravity do no work on the object because they don't. It's supported by the floor, and we're not pulling it off from the floor. The force F does do work on the object, but it's only the component which is in the horizontal direction. And so we're going to talk about this, doing that, and that's defined as the scalar product of two vectors. We start off with this kind of a diagram. So this would have been the distance along the floor that the vacuum cleaner is moving, and B would have been the force supplied by the vacuum cleaner suction cord that's going to pull the object upward. So we have A dot B is defined as, this is a definition, what it means when we have a dot product between two vectors. That's going to be defined as the magnitude of A, notice that it isn't bold-faced now, times the magnitude of B times the cosine of theta. And how would you get A? Well, you would use the Pythagorean theorem with the individual components of A, and the same thing with B. You would use the Pythagorean theorem with the individual components of it. And cosine theta describes that angle between the two vectors. And you can see that B cosine theta corresponds to the component of B, or the component of the force, which is in the direction along A. Okay, let's make sure I use the right kind of symbols. Okay, we also call this the dot product because of that use of the dot between the A and the B in our symbology. And remember that it's defined as AB cosine of theta, where theta is the angle between A and B. All right, and it's the minimum angle, not the one that goes almost 360 degrees around the two angles. And so this angle theta can take values between 0 and 180, but it can't go above 180. It doesn't matter which order we do the operation, because A dot B is the same thing as B dot A. And you could see that's true just by writing out what B dot A is. It'll be BA cosine of theta, but those are regular numbers, and in regular algebra with numbers, they commute when we're doing a product. Okay, and it also obeys the distributive law of multiplication. That is, if we had A dotted into the sum of vector B plus vector C, we could write it out as A dot B plus A dot C. Okay? Whoops. Don't want to be there. Okay, if we do the dot product of vectors, I dotted into I is 1 because it has the angle between I is 0, and the cosine of 0 is 1. And 1 times 1 times 1 is 1. On the other hand, if we have I dot j, the angle between I and j is 90 degrees, so that the product works out to be 1 times 1 times the cosine of 90 degrees, which is 0. And that's equal to 0, because 1 times 1 times 0 is 0. If we're going to do our dot product with components, here's how it gets written out because of the law we just gave you above. You would think that when you multiplied A times B, you would have a total of 9 components, because we've got A times all 3 of these, and the A sub y times all 3 of these, and the AZ times all 3 of these. But 6 of those components go to 0 by the argument above, and the other 3 go to 1. So we're left with this simple equation here, and that helps us when we need to find an angle. So one of the things we might do is try to find the angle between vector r and s in degrees. So we go back to our definition, and in this definition, A is going to be r and B is going to be s. Okay? We could have switched those because of the commutative law of multiplication. It would not have mattered for the dot product. So we'll get A dot B is equal to A sub x, B sub x, plus A sub y, B sub y, plus A sub z, B sub z. And that'll be a number, a scalar. That's why they call it the scalar product. By the way, A cross B is not the same thing as B cross A, so what I'm telling you about the dot product doesn't extend to the cross product. Okay, so this now gives us the way to solve for cosine theta, because there's the formula for it. And if we need theta, we would just take the arc cosine of that quantity on the right. And here I've left myself some room to do the math, but I'm going to stop here and see if what I've written so far makes any sense, and then I'll do another presentation which has this and the last part of the class for today.